Good morning, good afternoon, good evening, depending on where you're tuning in, and welcome to Mathematica Experts Live, Dynamic Interfaces Q&A 2012. Over the next 90 minutes or so, we'll be taking your questions about building dynamic interfaces inside Mathematica. We'll learn how to use the dynamic function. We'll take a look at how to build custom buttons and toolbars and how to build complete interfaces inside Mathematica and a whole lot more. You've already submitted a bunch of questions when you've signed up. We're going to try to get to as many of those as we can. You can also submit questions live in the Q&A pod on your screen, and we'll get to those as well. Now, if you have to leave at some point during the show, we hope you don't, but if you have to, we will have this available to watch on demand on our website. Check out in a few weeks, and we'll have that available. We'll also have all the notebooks available from these guys, our Mathematica experts, so you can play around with the code as well. I'm your host, Zach Barcel, and joining me, three of my colleagues, the Mathematica experts for today, and we'll introduce them starting at the far end. He's back. He was here last time, Yu-Sung Chang, followed by Faisal Whelpley, one of our newcomers to the program, and then finally Chris Carlson. These guys know dynamic interfaces in and out, and I know they're anxious to answer some questions. So are you guys ready to go?
Sure.
Yu-Sung will give you the first question. How do I create a simulation heat flow in Mathematica?
Okay, I will show you how to do that. So, well, I just took the typical, very simple heat equation. It's just an example, but you can do more sophisticated thing with your own equation. So, first of all, you want to start with the differential equation solver. So we have a D solve and we have an ND solve, and the difference is ND solve is a numerical differential equation solver. Usually faster. If you don't need a really accurate or symbolic answer, ND solve is kind of a good choice for animation and these other tasks. So in this case, it's a heat equation. The typical of the heat equation. You can see that we have a function over time and x and y. I use the two-dimensional one, and I will make it a little bit more readable. I use the key command Control-Shift-N, which turn everything into the standard form, which actually in return look like what you might see in textbook, for instance. Initial condition, everything is 0. The boundary condition in two sides, it's just fake example. So I use the sine t. Let's say that just fluctuating temperature outside. The other word, let's say temperature is 0, and our u is our function. The time is between 0 to 10, and the area of our the computation is x and y between 0 to 5. And let's quickly solve it. And this is a typical form that you are getting from the ND solve. And how you use it is, there's a couple of different ways. It's actually people's preference, but one of the way a lot of Mathematica users do this is like this. So let me assign that. I already assigned the solution as a solve, and I do this. So the idea here is this slash dot means replacing. So essentially what's happening is, it replaces u with this interpolating function, then you feed it with the x, y, g value. So let's see how it looks like. And of course, now we have 3 terms, x, y, and t, right? And when you want to do the animation, the t is the value you want to move. So let's fix one t, let's say 5 in the middle. And x and y varies. Of course, I have to do replacing. Usually I forget that quite often. And let's do this. And voila, you see the the temperature higher in the two words, and it propagates in the middle. Now, very neatly, we can just change that time using our slider. So I will point out there's a couple of problems with this approach. So, okay, now our t can be varying by this very simple command called manipulate. What it essentially says is, I want to vary the value t between 0 to 10. And okay, you can easily animate. So you see the propagation. Okay, I'll point out a couple of things. If you see the g-axis here, which represents temperature, the problem here is it changes. So in Mathematica, the way of plotting thing is, you have a tight. It always tries to make a very tight plot range. So if your function varies from, let's say, -1 to 1, it doesn't go that far. It just clip that area. So in this case, animation case, it's bad because it's kind of fluctuating. So I want to fix the plot range. Let's say plot range between, and I know that my temperature was sine function, so probably -1 to 1 is enough. Now I just fixed the, the G range. See, it doesn't show the fluctuation. Now I will make it a little bit more interesting by adding the color function. And well, obviously it's a temperature, so good choices. I mean, by the way, we have a set of the color functions, color schemes that you can use in scientific visualization. And we have a lot of different things. And one of the good thing here is the, let's try the thermometer or temperature map. It would be also good. I will choose the temperature map. Okay, so it worked. And you can see higher temperature. Now, here's another slight problem, because now the color function scales itself, meaning if you have a plot ranging from -1 to 1 or another plot ranging from -2 to 2, it always scales itself in such a way that the bottom value, the minimum value is always the last color, and the top value, the maximum value is always top color in the gradient bar, which is also, again, not good for our case because we want to be very, flat across this cross section. So one way to avoid that is color function scaling function. So essentially what it does is, instead of scaling your color according to your minimum and maximum, it just fixes it. Now another problem, now the color function in all those a lot of maps only takes value between 0 to 1. So you have to manually, unfortunately, rescale that. And I will just show you code. I mean, to see the detail, I would refer people to take a look at the documentation, which has a good explanation how it works. But quick example in here. Okay, let's say. For non-users, it's a mathematical way to write down a quick function. It's called just pure function. And number 3 in this plot 3D case means a g value. Now +1 divided by 2. So essentially, I know the range is -1 to 1. I just made range 0 to 1. So if you see this, now the neutral value 0, no temperature, goes up red, goes down blue. Everything works fine. And let's change it to the density plot. And in density plot case, G value is always number 1. So, and you can see more nice visualization. So, and you can animate it easily. So this is how you do it. And I suggest people who are interested in this type of scientific visualization visit our demonstrations.wolfram.com. We have many these equation solving and how visualize it, especially wavelet equation and heat equation, everything of those sorts. So I think this is it.
No, yeah, great. Yeah, if you want to check out some of those demonstrations, it's demonstrations.wolfram.com. You can find the link also at wolfram.com. All right, Faisal, you're up next here. We'll get to the second question of the afternoon. And what is the difference between module and dynamic module?
By the suggestion from the name, module and dynamic module are somewhat similar. Basically, these are scoping constructs. In Mathematica, you can create a variable and then assign it to a value, and this value can be repeated everywhere the variable shows. Module allows me to recreate the variable of the same name but prevent it from inheriting this global value. Similarly, any changes that I make inside is not going to be passed on to the global value. So module and dynamic module both work in the same sense. But as the name indicates, dynamic is the difference. The difference is how they scope this variable locally. One is a kernel history session, whereas the other is front-end session. That's the general rule of thumb. And anytime you try to do something with dynamic, and you want to scope your variables, most likely dynamic module is what you are interested. Module is more for evaluation purposes, not for dynamic purposes. Let's go ahead and see some concrete examples here. So module, the way it localizes its variables, and you can actually see the form that the kernel maintains for that matter versus dynamic module is slightly different. So if I try to create a dynamic in here, let's say with a slider, which will vary my value of x, there's some red indicators here in the syntax coloring, sort of indicating something might be going on, but the slider works just the same. And even in my dynamic module case, it also works the same way. So it seems to be no problem here. What happens, this is an interesting case, if I copy the output. So I create a duplicate of my module slider, and when I move one of these new sliders, you see the other sliders also moving at the same time. Even though these are scoped variables in the kernel, they are stored the same way. So both of these are dynamically linked. As opposed to copying the output from my dynamic module, if I duplicate this output, because of the way it localizes the variable, it is now localizing this independently because of the dynamic module. So this is a fundamental difference between module and dynamic module. And also, like I've been saying, module stores its variable in the kernel. So if I happen to quit my kernel session, in essence, I've lost that localized variable in the module. So now my module slider is not going to be very responsive. But my dynamic module is still responsive. What this means, I can save this notebook, send it to somebody else that obviously is not sharing the kernel history with myself, and they'll still be able to interact with any interface examples that I use. There are more examples such as this in our documentation center. Which clearly illustrates what the purpose of each of these functions are, and also tutorial to further explain what the difference between these two constructs are. So again, to reiterate, module and dynamic module, the main difference is how they localize. They are both localization constructs, but how they localize, where they store the variable values. Module is for kernel and useful for evaluation purposes, and dynamic module is stored mostly in the front end and useful for dynamic and interface constructions.
No, fantastic. No, that's a great way to sum it up. And if you want to look at some of that again, go to the documentation center and you'll find it all right there. Chris Carlson, you are up next, and we have a good question here. My dynamic is slow. How can I make it faster?
Okay, that's a common question. And there's one important principle that you can obey to make many dynamics faster. Let me give an example of that. I'll start with an example. Let's make a graphic which has a disk that I can rotate by means of a manipulate. Now, everything that I say here, although I'm using an example with manipulate, pertains to dynamic and manipulate as well. Manipulate implicitly wraps its contents with a dynamic. So let's make a graphic and put a disk in it. And I'll position the disk at cosine A, sine A, and give the plot range of the graphic, say, 1.5, so I have a little room to move, and let A go from 0 to 2 pi. Let's make that disk smaller, give it a radius, say, of 0.1. Okay. Now I have a disk that I can move with the slider. So this manipulate is nice and zippy, which is good. But now let's make a change to the graphic. Say I had a complicated background in this graphic, which takes a while to evaluate. I'll put that in here. Let's make a bunch of lines, say, lines that go from, I don't know, from what, minus 1.5 to 1.5. See if I did this right. There we go. And let's make a table of those. And I'll put 1,000 lines in here so that it takes a while to evaluate. And let's also make those lines gray so the disk doesn't disappear into the background. Okay, so now I have 1,000 lines in the background, the disk's in the front, and if I move the slider, it's a little jumpy. And you can see the background is dancing around. That's because every time the slider moves, the entire graphic is updated. So how can I make this faster now? Well, the trick is to wrap the disk, which depends on the value of the slider, with dynamic. And now when I move the slider, the disk is fluid again. Now the reason this works is that when I move the slider, the Mathematica says, oh, the disk depends on the value of the slider, so it updates the disk. But the disk is wrapped in its own dynamic, so when it goes to look at the outer dynamic, which is within the manipulate, it says everything's already been taken care of, there's nothing more to update. So it doesn't recompute that complicated background. So the principle here is always wrap your dynamic around the smallest amount of evaluation possible. In this case, the disk is the only thing that depends on A, so you wrap the dynamic around the disk and it makes it faster. You don't get unnecessary updates. So let me expand on that just a little bit. Sometimes you have a dynamic or a manipulate which is not quite fast enough to be interactive, but is fast enough to be manipulated. And there's a way of dealing with that. Let's make a very simple manipulate, which just manipulates a value x. X goes from 0 to 1. So now I have a slider here. And let's make it artificially slow by putting in a pause here and say pause half a second. Now the slider is sluggish because it takes a half second for every update. So there's a nice construct for making this responsive and at the same time giving you the results you want, and that is control active. So if you wrap control active around the contents of the manipulate and give it a first argument, I'll call it, say, updating. Now what happens is, when the slider is in motion, you see the first value of the control active, and when I mouse up and let go, it evaluates the second argument. So I can move the slider fluidly because it's not doing the update of the slow code, and then when I mouse up, I see the result, which takes just half a second, so that's just fine. That's a very handy construct to use. If you would like some more information on how to make dynamics and manipulates faster, if you go to our courses, Wolfram training, it's online, and there are a few courses that might be helpful. One is, let's see here, visualization, advanced 3D graphics. Another one would be interactivity, building an app in 60 seconds. There's another one, Yu-Sung?
Graphics and numerics.
Let's see. I think that'll do it. So there you go. That's how to make your dynamics faster. If you just pay attention to that one principle, you'll have much more responsive interactivity.
No, great. We have a follow-up question from one of the viewers. How come Chris's indentation is jumping around as he types? I've not seen that before.
My indentation is jumping around. Let's see.
It was while you were doing the first example there.
So Mathematica does on-the-fly formatting of your code. I suspect that's what you're seeing. If I, for example, remove, yeah, okay, that's probably what you're seeing. So in this case, there's a list here, and if the list is open, it thinks that that you're indented perhaps another level than you actually want to be. When I close that list, the level of indentation corresponds to the structure of nested objects in that expression. So it's going to jump around depending on what what sub-elements you have open or uncompleted or not. Why you're not seeing that yourself, I don't know.
Chris, are you manually inserting new lines when you type code?
Yes, I do.
Maybe that's why you're noticing the automatic indentation.
That could be. Yeah, I always use a lot of new lines. So if you don't use new lines, perhaps that's why you're not seeing this change in indentation.
No, fantastic. A great example, and hopefully that answered your question as well. All right, Yu-Sung, we'll get you your next question here, and it's a fun one. How do I create financial interfaces with Mathematica?
Yeah, and hard one too. It's depends on what you are expecting to see here. So I can think of a couple of other cases, like a finance interface. One would be one of those typical stock chart and these things. Other would be something you would see in, the what is it, the retirement plan or these type of things. How interesting this thing works, and I will use this opportunity to introduce. I mean, it's not exactly interfaces, but other supporting functions that Mathematica have that's important here. So I will show you some of the good thing about Mathematica in this financial area. So first of all, the quick answer: if you want to get this, typical stock chart type of thing, you don't really have to working on that because we already have our built-in function just doing so. For instance, I just want to see, past couple of months the Google data. Then we have some chart called the trading chart, and it's not just showing good example, but it has a lot of dynamic interface elements. So if you mouse over, it shows a high, low, and when it happened, and the volume at the bottom, everything happens. Now, I mean, it's not the only chart, the information you want to get out of there. There's a lot of the moving average and a lot of other information you want to get. So trading charts support something called a financial indicators, but you have to find it in the manual or the documentation center, and you go trading chart and you will see all these different indicators. However, more easier way is using something called the interactive trading chart. So this is our another function, a bit more sophisticated, actually quite more sophisticated. So looks similar except that it's quite dynamic. So in a sense that it refreshes itself, and you can choose to see a different window of the time period. Like I want to choose a city here. Now another good thing is you can choose to see all different indicators. So it's on the bottom. We have a selector menu. You can add, for instance, a typical one. How about Bollinger Band? It's moving average on the high and low, and it shows nicely on top of the plot. So, okay, this is one way to do the task, and many times it's probably enough. But let's say you want to do things by yourself. So I will show you quickly two examples. One using financial data, the other one using the more traditional time value data. So one thing, financial, the Mathematica supports something called a data packlet, which means you get a real time or some data from our best amount of this repository, and starting from Mathematica A, you also are able to get the data from Wolfram Alpha too. In this case, financial data, I'm trying to get the data from about the Google stock price between 2012, the January to until let's say July, and I will assign it to the data. So you just get the nice data. As you can see, the data format is pretty straightforward. It has a timestamp and a value, timestamp and value. Now, these type of data, how you want to display it, we have some function called date list plot. So it knows how to interpret the date, for instance, and what's data. So you don't have to actually say anything. Now, quickly, make a dynamic version of it. You can wrap it around with the manipulate, right? So and let's say data, I want to just display data from certain n, and n would be depending on the length of the file, right? So length of the data. So I would just want to display a portion of it. And okay, I have a same mistake here, but one thing you have to notice is that the slider, the manipulate slider, moves continuously unless you say not to do it. So in this case, I'm taking this is a part command. I'm just taking a part 1 to n, but n should be integer, so I want to move it by 1, incremental 1. And you can see it just shows dynamically the reason of these things, and you can add a lot of different functionality here. Now let's move on to the slightly different topic. So another one, I love this function because this time value function added in version 8. Before that, whenever people ask, for instance, I have a certain money in the bank. I mean, I try to use Mathematica in a lot of different areas. And, for instance, quickly computing, for instance, my mortgage and this, I try to use Mathematica. Problem, the computing the interest rate and these things. It's just simple, like a geographical, geometric sequence, but still it's bothersome. Sometimes people have a different way to compute it. Now, version 8, we have this built-in function called time value, which is pretty handy. So let's say you have a $10,000 in your bank, and your interest rate is, annual interest rate is 0.83, and after 2 years, how much you got, and it just computed for you. Now, I will make a very interesting plot out of it. So let's say bar chart, and I want to see a 10-year trend of this, how my money is growing. Yeah, let's see. Actually, you know what? 3% is too low, so I'll make it 6%. And let's say from year old to 10 year. And let's see. The bar chart is nice, so you can see this. Now, why don't we do it with a manipulate? And I will make the endpoint as, let's say, D, maybe. And D varies from 2 second year to, let's say, 30 years. So it's a long-term plan. So you can see, how it changes. Now, I will play a little bit more. How about we want to change the interest rate too? So let's say interest rate varying from 0 to 1% to 10%. And let's see how it changes. And you know what, actually, this has to be, that's a slight, one interesting thing about this time value is it's not actually the date, can be a continuous value. It doesn't have to be discrete value, but I can just make it discrete. So now, at interest rate 0.1% of interest, it's not that interest. You start with the 10, after $10,000 after 30 years, you only make 13,000, but interest goes up. At the 10%, see, the amount of money is now, you have a one more digit here. So this is one way to visualize this financial data. And I think this question actually includes some of the way how you're gonna, in real time update this data if you have a data stream. Actually, the problem here is actually the quality of the data, because a lot of these financial institutes, the free service, they don't like you to bang their service and grabbing data every second. So, but if you have some premium data that the data source, that I would just quickly show, it's not really full code or anything, it's how our dynamics works. If you want to refresh it, for instance, every second, I'm just using string, the date example. I will just assign every second, I will refresh the data. So, as you can see, the counter is tickling, right? So essentially, you can put your finance plot or whatever the grabbing data part inside this structure, and it will update itself every second. And I will refer you to the one of the to get some more inspiration about what kind of things you can do with the especially in the financial area, our CDF example contains the investment statement and typical report, financial report type. I know also that's a big area, so you can see we have a embedded report here. It's actually moving dynamic report. You can change the range and such. So this is a good examples, and I think we provide a source code upon request. So that's a good way to learn things about finance.
Fantastic, Yu-Sung, thank you very much. All right, Faisal, you're up next again, and here's a fun question for you. Where can we find source code examples for full-fledged Mathematica interfaces?
I can interpret this question in two different ways. One is writing Mathematica interfaces. As you've already been seeing, we've been doing using manipulate and similar constructs. We have a website dedicated called Wolfram Demonstrations, which has tons of manipulate examples in a variety of topics. All these manipulates are written by users, contributed through us, published on here. And each of this demonstration comes with the source code, which you can download and interact with your Mathematica. Or even if you don't have Mathematica, you can install a CDF player and still interact it via web browser or desktop. So here's the source code, for example, that produced this particular interface. And every single manipulate on this demonstrations website come with the source code. That's one way to interpret. The other way is to think of interfaces that come up within Mathematica itself, for example, dialog boxes and toolbars. I'm going to bring up our documentation center again and do a search for interface, because Mathematica comes with really heavy documentation on a lot of aspects. It is a very general program, so there are a lot of topics to cover here. Custom interface construction contains introductions to manipulate, control objects, all the different control objects that we support, views, and if I keep scrolling here, there are two sections we don't want to touch: introduction to toolbars and creating dialog boxes. And they come with their own extended example. So if I click on the word processing toolbar here, there's some text to guide me along on the construction of an example word processing toolbar. So I'm going to go ahead and evaluate this code, which is in the documentation center, and sort of see what the final result is. So I'm evaluating this in sequence so that everything gets picked up. And finally, we have a window creation here, and I have this mocked up word processing toolbar in my example. So I can start entering text. I'm pretty sure these are functional as well as pretty as they are. And there we go. So those are toolbar examples, and as I showed you already, there's also examples on creating dialog boxes, all the elements that would go into a dialog box creation, palettes, creating palettes, and they have extended examples providing source code for all these different types of dialogues and palettes. Now, a lot of Mathematica dialogues are in fact created in Mathematica themselves. So if you want examples of things that you can do, you can look at something like the welcome screen, for instance. This is a Mathematica notebook written entirely in Mathematica code. So it just gives you an example of the kind of things that you can do in Mathematica itself. The source code, particularly for this example, is not available publicly, but the ideas to construct such a interface is definitely within our tutorial.
No, fantastic. Yeah, there's some great ways, and dig into some of those examples, and hopefully you can do one of those too. All right, Chris, another question for you here. Is there a way to control the layout of input objects in a matrix format?
Yes, there is. Manipulate has a lot of flexibility in laying out controls, and there's almost never any reason to use anything but manipulate to put together an interface. But many people are not aware that you can go beyond the standard layout functionality. And let me give you an example. So let's say we have a manipulate of a grid of values A, B, C, D. Okay, and we want to fill those values with sliders. So the standard layout would be like this. Let's say we have A goes from 0 to 1, and let's duplicate that 4 times, make B, C, D. Okay, so now I have a matrix whose values I can control with sliders. Now, suppose I want to lay out these sliders so that their arrangement is a matrix which corresponds to the arrangement of the grid that I'm manipulating. So the way to do that is with a control object. So I can lay out, I'm going to copy this grid, and I'm going to use the same grid to lay out the controls. And each control object is wrapped with control. You just take the regular specification you would use to specify the parameter value of the manipulate, wrap it with control, and drop it into the grid that you're constructing to contain the controls. So I'm going to replace all of these values here with slider controls. And then I'll go back and change this to B, C, and D. And there you go. My controls are laid out the same way that the grid is. You can put any kind of annotation in line and the controls of manipulate. For example, you can say, let's put a label in here, style controls bold, say. Okay, get the label in there. You can also put, for example, delimiters. Let's make a dummy control just so the delimiter will show up. Okay, you see here I have the gray line delimiter. Gives you a lot of flexibility for laying out controls. There are also some options you may not be aware of which don't pertain to matrices but give you flexibility in arranging the controls relative to the content of the manipulate. For example, say we are manipulating x, y, and x and y both have controls. Suppose I want to put the y control below the content. There's a control placement option. Control placement below, bottom I think it is. There we go. You can put controls left, right, bottom, top, and so forth. There's an interesting example in the documentation. And I'll segue into the answer to another question which has come up often, and many of you submitted this question, and that is, how do you dynamically change the set of controls within Manipulate? So I'm going to go to the Manipulate documentation. I know that there is an example in the Need Examples of doing that. Here we go, Need Examples. And there's an example of this one right here. I'm going to pick it out and go back over here to my notebook and pop it in there. This one shows you a matrix with black and white pixels, and you can change the number of pixels with these sliders. And you see that the controls here for the pixels, if I check these, things turn black or white. The controls, the number of controls is controlled by these sliders. Now the way you do that is, let me improve the formatting here a little bit so we can see what's going on. Okay, so we've got, first of all, the data from which that image is built. The data has control type none. What that means is the data is localized to the Manipulate. The Manipulate knows about the data and knows to update it, but there's no control associated with it. And then I have the H and W sliders that correspond to the height and the width of the array. And then this dynamic here, which constructs a panel containing the checkboxes. By wrapping that panel with dynamic, it responds to changes in the H and W sliders. And then the contents of the dynamic, this is slightly tricky. You cannot use the control syntax because Manipulate doesn't know how to deal with arrays, array references. It's only set up to deal with individual variables. But you can explicitly specify a checkbox, give it an argument, which is a dynamic, and that checkbox will work in the context of the Manipulate. So remember this example. If you want to do this kind of thing, you can probably easily go back to that documentation and modify it to suit your purposes. There you have it. There's a lot of flexibility in Manipulate for configuring interfaces just exactly how you want them.
No, you're certainly right on that one. And in case you are tuning in, you can download these notebooks as well that Chris was just playing with. We'll have those online as well. Well, we will also have this entire video you can watch on demand in case you have to step away. Hopefully you can stick around. We're about 40 minutes into it right now. We're going to go all the way for another, about 40 minutes or so. So stick around, a bunch more questions to get to, and have some good ones coming up here. And Yu-Sung, we have some great questions about the computable document format, or CDF, here for you. So let's first start off with, what are the advantages of CDF for dynamic interfaces?
That's actually two separate questions. So what is the advantage of CDF for Mathematica users who are already using Mathematica? And the other one could be, what is the advantage of CDF overall in general, right? The people who may not use Mathematica, but it's some people complain it's another format, right? We have a PDF, Flash, and everything, but why bother with the CDF? So I will try to address both of them. First, to start with the in general question, why CDF? So a little bit too marketish, but I will try not to sound like that. But we actually created, when we developed the CDF format, we did some sort of a comparison with the other formats. So here you go. So this is a page under our wolfram.com/CDF, and you can easily navigate and find this particular chart. So overall, I mean, for me, in particular for Mathematica user, or even just a general technology person who actually had experience of making the web page using these dynamics, for me the real the benefit of the CDF is, first, it's a more integrated format. The graphics and the formula and everything, can be in single format, and you can share it with everybody else. And then another real strong part, I mean, that's why actually I love CDF than anything else, is the computation. Because behind the CDF, you are essentially getting the Mathematica. So you download the CDF player, and the computation power is almost equal to the, with a small limitation because it's free, and there's a security issue on the website. But except that, it's almost what you're getting with the Mathematica. So for instance, I showed in previous example this type of financial chart and computing time value in these things. Think about implementing it for your company, for your school, in using, let's say, JavaScript. The problem is, Yes, JavaScript as itself is a language, but it doesn't contain these different libraries. You have to find those libraries, find those, for instance, that NDSO. It's hard to find actually, and also maintaining speed. So that's real strong part of the CDF. It comes with all these different computational pieces in single framework, and you can easily put them together. Now, for Mathematica users, obvious benefit is you can share this with the people who might not have a Mathematica. Of course, it would be great if they also have a Mathematica, but sometimes it happens, right? So I will quickly show you. And then I am actually seeing another question about how easy to turn this normal notebook into CDF format and such a question. So I think this is a good opportunity to introduce it. But we already have a separate, the virtual conference about this CDF, so I will introduce that later on once I explain this. So let me start with a very simple plot like a sin x. Now, I want to, make it just like, before. I want to make it manipulate, so I will change the frequency, all right, 8, 1 to 10. Very simple way to make it, and, it's not bad either. And, let's make it much more interesting. I mean, not much more, but slightly more interesting. So I will add a shifting part to here. So as you can see, you can move it around, you can change the frequency, and so on and so forth. Now, I want to share this with, for instance, I'm teacher. I want to share this with my student, who might not have a Mathematica. That's where CDF come in play. So it's a great way to turn these notebooks, the one that you're using, into the shareable, the web resource. So the way of creating CDF file is very simple. I think that was also another incoming question. Boy, today we are getting a lot of questions here, so it's very hard to catch up. But as you can see, file, under the file menu, you can see there's a new menu in version 8 called deploy. Now you can choose to make it as a standalone. What it does is it saves as your notebook as a .cdf file. Then you can just send it to the people who might have, using email or whatever. And then only thing they have to do is go to our site, like wolfram.com/cdf, and download the CDF player. Then you can open this just as if it's a Mathematica notebook file. Of course, this free CDF does not allow you to modify the contents. It's just purely view only. Now, well, I want to just embed into the my website because I guess a lot of people already seen our demonstration page or blog page where we have this nice embedded CDF, for example. Someone like, you can think of it as someone like a Flash, like an embedded one, but a much more powerful Flash, I would say. Now, to do so, there's another option called the embedding HTML. I will just try to follow that line. So it has a nice visual setup and it describes what it is. Continue on, and I have to choose where to save it. So let's say it's under one of my directory. I will name it sign.cdf. Continue on. It asks, okay, it's embedding, so I need to have a HTML file which will embed this one. And it will be in the same directory. Then it create a embedding code for you. So I will quickly cut and paste it. Okay, cut. Now I'm opening up my, the text editor. I will make a very basic HTML structure. Close it. And well, to make sure it is really embedding, I will put some title, right? Sign plot. And embedding the code, then I put the some description. This is a sign plot, and you can change A and B, just for fun. Now, let's see how it works. So I just create that file. Let me bring up the web browser. Where are you?
Yeah, we just had a question come in. Are CDF documents easy to display on web browsers?
Yep. So that's what exactly I'm trying to do. Okay, I just create this HTML file, and voila, that's what you see. So, of course, if you don't have a plugin, of course I do have plugin, but it'll ask you to download the plugin. It'll say that, the Mathematica plugin is available in such and such. Then you click, the user click it, then you'll be able to download it. Now, this is one way, and there's an additional question about import and export the images into the CDF. Okay, it's a very tricky question because a standalone CDF, just I described, the one that you can share using, that allows accessing of resources, but only through the web, because that's a security issue. Wolfram doesn't want arbitrary program to access your files, for instance. Who knows what kind of some ill thing that it can do. So that's a security issue, and we have our sandbox. So the CDF, the shared CDF, cannot go to your local machine and access this data. Although you can still access the resources that are available through the web, like HTTP/. So I will give you one quick example, which I already used in our one of the special event. Okay, it's gonna be a little bit tricky to find it for me. Okay, here's one example. So this is one typical example of using external web resources. I'm getting this data from the NASA's Hubble Gallery. The images are humongous, so I cannot include that in my CDF file because the CDF file itself can be a couple of megabytes. I don't want that. So it load up each images whenever people open up. Now, when that happens, like importing these things, some security issue happens, the CDF plugin will ask you whether you want to really do that. So this is what warning you're getting, and I enabled it. Then as you can see, it's right now, in real time, getting the data from the NASA. And these are just thumbnails, but actual images are very big. It's like everything is like 4 or 5 megabytes images, but we have a fast connection here. So this is one way, and it's very deep issue. There's a lot of interesting you can do with the CDF. I would suggest you to go to our training site. There's a tab called Special Events, and you will find that there's a CDF virtual workshop, the history. We go there. We have a lot of good courses. The general overview, the John McCullen's course is pretty nice. And how to embed things in the web, the Vitaly's course is excellent about that. And in my course, I describe more these top level, the higher level things, like how to include these external resources into such.
And another question that one of our viewers has asked, would CDF be a viable format for publishing a math textbook? And on our CDF examples page, we have an example of that.
And in fact, I was just trying to tell that. So
there we go.
In the last talk in this CDF, the virtual conference workshop, we have Eric Short. He actually worked with the Pearson, this one of the popular calculus 101 book, Cochrane book, which we turned into the CDF. I mean, he turned into the CDF format, and it became quite popular. So I will show you what example it is. Okay, not here, but we have a couple of chapters from the book. It looks like this, It's a very nicely written book. And actually, in the course, he described how he did it and what kind of material he used. So that would be a really good start for who are interested in, publishing their own book in CDF format.
No, fantastic. If you want to learn more about CDF, it's wolfram.com/CDF. All right, that was a great example of many examples on how to use CDF. So I know that Faisal, you've been waiting here for a few questions. We'll give you a couple here. Can I insert dynamic elements, meaning opener view or input field, into a function plot? And then, can I add a mouse over event to a UI?
Why would you want to insert dynamic elements into a plot? Well, dynamic elements are fine. If I have sine x, and here's a plot of it from 0 to 2 pi, I can insert dynamic elements, let's say a tooltip. So I can wrap sine x around with the tooltip. And what that will do is automatically label this curve with the function itself, which becomes very handy if I have multiple curves. I can also create go back to my sine plot here, a label that possibly queries my mouse position. So now I have a dynamic element as part of my plot, which just tracks where my mouse is on the screen. If you want to insert, so these are dynamic elements, meaning it's just a view. If you want to insert control elements, well, yes, you can do that. Most likely you want to create a dynamic module construct. So I'm going to create a dynamic module here. And what I'm going to be interested in changing my function that's being currently plotted. So I'm going to initialize that to sine x and create my plot. And in order to insert the dynamic element, I'm going to create an overlay so I can stack the plot and the control element on top of it. I'm going to start with the pop-up menu first because that's an interesting example. So the variable that I want to dynamically change is f, and give it a few choices: sine, cos, and tan. Mismatch brackets here. So that will give me a starting point to create a pop-up menu inside my function. It kind of looks ugly, and there's one more thing. This pop-up is not currently interactive because I'm not completely specifying the overlay syntax. So the documentation for overlay allows me to set which control needs to be active, which overlay needs to be active. So I want to display all of them, but only make the pop-up menu active. So yes, now it is still not working. I'm able to interact with the sine x, but the plot isn't changing because I need to make the plot dynamic. I have the dynamic around the plot. Now the pop-up menu is interactive, and my plot is changing depending on my selection. Again, having that pop-up over that plot is rather, I don't know, it's not very pretty. But I can change my pop-up menu to something else, like what the user was initially asking, for instance, an input field. And if I get the correct syntax for input field, which is just the dynamic variable that I need to update, now I get to enter any function that I want. It can be cosine, tangent, or even some other function. Of course, because now I'm able to enter any function I want, I could enter something that Mathematica can't interpret correctly, then I won't get a plot.
But that case, you might able to use Wolfram alpha, for instance, get the correct function name.
There are additional things that you can do,
Right.
but that involves the user writing
Right.
their own program for doing that. But that's a limitation. There's also an advantage because I can enter anything I want.
Right.
I really can enter anything I want, which in this case I've just entered a list of two functions. Now I'm able to plot simultaneously two functions at the same on the same plot.
And I believe you can overlay that thing in the middle, for instance, if you want. It doesn't look good, though.
Exactly. You can move it around, and in my opinion, in my humble opinion, moving this any place is probably not going to look really good. I can align it so that it shows up in the bottom of the plot. Still, it's sort of hiding the plot. But an interesting side point to this is the follow-up question: can I add mouse over events to my UI? Because we have a function called mouse over to do precisely that. So I'm going to take my input field, which I didn't quite like the placement of it, and create a mouse over that will show the input field when I am moused over it, and when I'm not moused over it, it would make the input field invisible. Yes, invisible is a function in Mathematica. Did I mess that up?
I think that's the other way around, right?
Look at that. I did it the other way
Yeah.
around. So when I mouse over,
Right.
I want it visible.
And
So now my mouse is not over the input field area, but when I go to the input field area, I see the mouse over, and it's still interactive, which means I can change the function, go away, boom, it disappears.
very nice.
No, fantastic. All right, a couple more questions here. We're going to skip the order to get back to Chris here for a second. Is it possible to initiate a different manipulate from within a manipulate?
Of course. You can do a lot of surprising things in Mathematica that people might not expect. So you can use manipulate to design manipulates. Let's look at an example. Let's make a basic manipulate. Our simple one again. Okay, now let's say I want to explore variations of this manipulate interface. So I'm going to wrap this with another manipulate. And for example, suppose I want to look at different control types. So in the second outer manipulate, I'm going to let type be slider or animator. Okay, so now the outer manipulate chooses what type of control I have. And the inner manipulate chooses, shows the effect of choosing that control. Suppose I want to play with control placement. So let's say I want the place to be left, right, bottom, top. And I'll put a control type, control position, placement here. Okay, and just to make this a little bit clearer, I'm going to wrap this inner manipulate with a pane to provide a little white space around it so we can see what's going on. I'm going to let the image margins say, I don't know, be 50. There we go. Now it's easier to see which is which. And now I can look at different control placements, see what happens if I use an animator or a slider and so forth. So yes, you can put manipulates and manipulate. Along the same idea of surprising things you wouldn't expect that Mathematica can do. Let me show you one more example. This is not necessarily related to manipulate, but it's something you probably may not be aware of and you wouldn't even know to ask the question. And that is, this is a way of making one-off mini interfaces from anything in Mathematica. I'm going to make one out of a mathematical formula. So suppose I'm doing the integral of 1 over 1 plus x to the something. Let's close that parenthesis, dx. Okay, and this something, I'm going to do this way. I say dynamic setting of pop-up menu. And I'll have an initial value of 1 and let it range over, say, 1 to 5. Okay. This is a way of embedding controls into any Mathematica expression. So I've put the pop-up menu control in this dynamic setting thing, and I'm going to select that sub-expression, and on the Macintosh use command return. On Windows it's probably control return. So I'm going to say command return, and it's going to evaluate, whoops, I got too many T's in there. Let's try that once again. So dynamic setting of pop-up menu 1, range 5. Okay, now I got it spelled right. The syntax coloring should have tipped me off that I had an error there, but I didn't pay attention to it. So now I'm going to command return that. Now I have a control embedded within my Mathematica formula. I'm going to evaluate this. I get the value for 1. What happens if I change it to 3 and reevaluate? I get the answer for 3. You can put any kind of control into any Mathematica expression, sliders, checkboxes, whatever. So it's useful for making just one-off throwaway interfaces. It's also useful in pedagogical situations. You can set up interfaces that are easy to explore concepts with.
No, great. Yeah, and definitely, if you want to play around with those examples some more, you'll have to check out that notebook a little later. Yu-Sung, let's get you a question here. Is it possible to plot solids of revolution?
Oh, yeah. Well, right. Of course. I mean, it's a good question. A lot of, the educational, especially elementary, and a little bit higher than elementary, solids of revolution or surface of revolution, which way you want to put it, it's an interesting topic. So yeah, I will show you it's both ways. I mean, the user just asked how to plot, but I will show you how you're going to animate it too. I mean, manipulate it too. So let's just start with the what you want to do. So we have a handy function called revolution plot 3D, and as you can expect, its revolution is rotating things, right? So I will show you how it looks. So t is the the value through the axis of revolution. So whenever that changes, it automatically rotates. So t, let's go gamma to 0 to 2 pi, and the degree that I will just call d, or should I say I should just call it d 0 comma, let's say it's rotating, so yeah, 2 pi, right? So we'll see how it looks like. It's not exactly what I wanted because the revolution axis is not right. I want to rotate it through the x-axis. So revolution axis, I will specify it as x. Okay, here you go. Look better now. It's overlapping itself, not nice. So I will add enough number to get it away from each other. Okay, it's more look like it, right? It's a typical, the solid of revolution stuff. Now, you want to have inside of it. Well, I think you can have something like this. Oops. Yeah. I mean, that's a mistake. No, you can't, right? So it did override that as a value of the other axis. So I will start with this one. And I think this is a good example because there's some more things you can play with. So let's make it and manipulate. Let's say I want to rotate it, but up to a certain degree. Let's say what would be the better value here? dd. I will just pick something. And let's say the dd can change. Well, 0 means nothing. So let's start with a slightly bigger than 0 number, then wrap it around at the 2 pi. You can see. And easily rotate the stuff, right? So you will see. Same problem as the previous example. If you remember, the plot range changes, right? It gets smaller, then you can, it wiggles. It's not that nice. So I will put some stoppers for that problem by just specifying plot range. In this case, it's tricky. So let me see what actual plot range is. Let me see. It's going to the okay. So 3. So 0 to 6, 3 to okay. So the x-axis can be all. The rest of them can be 0, minus 3 to 3. But I will give it a little bit of padding. So how about 4? There you go. Nice. Not moving. I mean, the plot range is not moving. Of course, everything is moving. Well, it's smooth, right? Now, can you change the actual, the profile cover? Let's say right now it's much more fixed, but let me add like A here. You can do anything actually. A, let's say 1,3. Too much wiggle, it wouldn't look that great. So increase. Now, more wiggle, right? Very interesting example. And one thing I learned, I have the elementary schooler, and kids love play with these things. Instead of just trying to describe what the heck the solution, surface of relation is, they just can play with it and understand the concept pretty easily. Now, one thing you would notice here, which is pretty important point in this, the mathematical graphics is, when you're starting to moving things around like this, you will see that the meshes suddenly disappear. And the quality doesn't seem to be quite up to the quality you would expect to see. That's how Mathematica deal with the speed issue. So if the case it's too slow or something, especially when manipulate, we have 2 decisions. Okay, make it slow, user suffer. The other way, we have an adaptive approach. When you control it, your focus is moving stuff, not actually, the final product of it. So in that case, we drop down the quality, which we have every plot functions have so because of that, we have a function called the performance goal, which is nice handy option. And let's say it's a speed. It makes things as fast as possible, but, it suffers in the quality sense. If you say performance, quality, then it gives you as high quality as possible. Let me make it a little bit more beautiful. Plot style, interactive. Usually the way to make it look good is using the specularity. Make the surface shinier. Range of 100, let me see it works. It might be the other way around, but the best way for Mathematica to try it out is just playing with it. And I don't think I need a mesh, so. Okay. Probably it was the other way around, so yeah. Graphical, so this is a command I want to use, right? The Y and N. Actually, you know what? I didn't specify original color. So orange is my color. The specularity, the shiny part is white color, right? That's right. Okay, you will see shinier surface. Much look better. It's high quality. It always is high quality because I just said, performance goal is quality. So it doesn't drop down the quality. But of course, it only works. It works smoothly only when you have enough computing power to compute these type of things. So.
No, great. We have a follow-up question too along the same topic. What about solids of revolution from a list of XY points?
Okay. Yeah, tough question, right? Well, it's I will just refer people person to the it's a little bit short of a time to describe everything. So. There's a great example. So yeah, this is a typical way to deal with this situation. So I mean, this is one of our demonstration example. Always you can go there and take a look at the code. It's a pretty simple code in this case. So it's a slightly different than approach that I just described, because it's a more industrial surface. It's not functional surface. That it's a parametric surface called a B-spline surface. So we already have function which handles that, and the way of rotating things is slightly different. Instead of actually using rotation controlling using degree, it actually has a special way to make a surface of a solid revolution. But you can see, you can change everything. Right? Actually, I love this example because it's quite fun to play with. But so you can change the profile curve in that scenario with this B-spline curve, or in this case you would use B-spline function or interpolating function with your given point. Then it'll just work like this. So.
Fantastic. And now, can you use the generated solid as an input to another step?
It depends on what that another step means, right? So if you're solely talking about using this graphically, I mean obviously, right? That's a benefit of Mathematica, right? You can do some funky thing like, I don't know how many people actually do this, but this is one beauty of Mathematica. Everything is I think I just killed. Okay, see. You just solved the multiple surface of revolution question, which might not have that much of meaning, but that's that's a beauty of the Mathematica. Anything can be anything essentially, So let me reduce this. See, and more fantastic thing, everything is moving,
Fantastic. No, some great examples there. Chris, you had something?
Well, yeah, I just want to say, Yu-Sung's being very modest. He made that potter's wheel demonstration, and if you go to demonstrations.wolfram.com and search for Yu-Sung Chang, you'll find lots of beautiful examples of how to make nice interfaces.
No, yeah, so some great examples there. We have a fun example here. Chris, how can I make best use of my laptop's accelerometers in building things like augmented reality interfaces, also cameras?
Yeah. Well, this is a fun question. Sometimes Mathematica is so fun it's hard to get any work done. It's an occupational hazard of working at Wolfram Research. Let me start with the accelerometers. So there is a function called controller information that will tell you what kind of devices you have hooked to your computer. And I'm working on a Macintosh, so you see down here there's sudden motion sensor. And if I open that up, there's a part labeled Mathematica controls. And I'm going to pick up my laptop now and move it around. You can see that the X and Z values are changing as I tilt my laptop. So that's the built-in accelerometer in the Macintosh. If you hook any kind of standard standard gaming device like joysticks or controllers, whatever, Mathematica will automatically recognize them, and you can use this controller information to find out what the devices are that you have access to. So if you want to use these, you look down here, you find out the name, sudden motion sensor, and you find out the names of the controls, X, Y, Z in this case. Now only X and Z actually update. So I'm going to use those now to control and manipulate. So let's make a digital level. I'm going to turn my laptop into like a bubble kind of level. And I'm going to do that by making a graphics. And the graphic will have I'm going to make something that kind of simulates a spirit level. So let's make an orange rectangle. And I'll make the rectangle go from, say, I don't know, minus 10 to 0. Let's make it minus 1. Minus 1, 0 to 1, 1. Okay, so there's a rectangle. That's a little bit thick. Let's make it 0.1. Okay, that's good. And now I'll put in the bubble. And the bubble will be let's say, a gray circle. And I'm going to position it at a horizontal coordinate x, y coordinate 0, and let's give it, let's make that 0.05, so it'll be in the middle of my orange rectangle, and give it 0.05 radius. And now let's let x go from -1 to 1. Okay. So now I have a device that I can control with the slider. Let's make that white. It's a little bit hard to see when it's gray. Okay, now I want to hook this up to my laptop's accelerometer. Well, I looked and found out that the name of the controller I want to use is sudden motion sensor, so I'll tell manipulate to use controller linking, sorry, not controller linking. So if you forget what the names of options are, for example, in this case, control, I know it begins with controller. I'm going to type controller star with a question mark, and I can get all of the options which are which start with controller. So what I really want is controller path here. So controller path, sudden motion sensor. Okay. And I have to tell it which of the variables in the controller to hook up to my manipulate parameter. I want the x of the controller to correspond to my manipulates x. And now let's see if this works. So I'll evaluate this, select the output, and it doesn't work. Oh, here we go. It's working. So I'm tilting my laptop now. It's just barely moving, which means I have some scaling problem here. I know what I'm missing. So by default, the controller uses relative values. What I want are absolute values. So the way to do that is using controller method and say absolute. And now I'll select the output. There we go. That's what I wanted. Okay, so now I'm tilting my laptop back and forth, and just like a level, that bubble's moving, and if I hold it perfectly level, I get the bubble right in the middle of the thing. So I've just simulated a spirit level. Okay, let's go on to move on to cameras now. So if your laptop has a built-in camera or a camera connected to it, you can find out using imaging devices. Okay, and this will tell me what I've got. I've got a built-in eyesight camera, and I can get at that using current image. So if you say current image, evaluate that, the first time you do it, it takes a couple of seconds to fire up the computer's imaging system, and there it just took a snapshot of me. If I wrap this with dynamic, it will update dynamically, and now you get a video of me. Okay, so what can you do with this? You can give current image an argument. Say I want the last 2 frames of the dynamic, or of the current image, and it'll take a little bit to evaluate, and then it'll get going. There we go. So now I've got the last 2 frames. Let's now take the difference of these 2 images dynamically. So I'll say image difference, and using the at notation means replace the list of 2 images with image difference of the 2 images. And now if I evaluate this, if the image is unchanging, the difference is going to be 0, or a black image. So that's what you see there. If I move, now you can see me moving because the difference changes. So in this little one-liner, I've made a motion sensor out of my camera.
Oh, that's fantastic. We had a user follow up with a question. That's great. What about microphone input?
Microphone input. Help me out. I believe there is a way to do it. It's not something that I've done
Yeah,
before.
we can record it, but I don't think at the moment, for instance, you cannot do something interactively. It's a limitation on actually sound card side, it's interruption and these things, So usually sound part is old technology. It doesn't work that well with the interactive technology at the moment.
Okay.
But yeah.
No, great. All right, time for a few more questions. Let's see. Let's go to Faisal. I've got a good one here for you. Can I extract data from a curve that was drawn by me?
The answer is yes.
Well, good.
So let me start by bringing up our drawing tools palette so I can start drawing some curve here. First, I'm going to insert a new graphic so that I have a blank canvas to fill in here. And I'm going to pick up a line segment and start inserting some points here that will make me a segmented piece of line. There we have it. Very pretty. I'm going to assign this graphics here to a variable and dismiss my palette. Evaluate that and show the way Mathematica stores the entire graphics. So the input form for this graphics shortened looks like so. So it's a graphics of a line with all the points that was required to construct this line segment. So if I like to extract the data, in this case, the list of points, I'm going to use a part expression, which allows me to dive into the curve here, and I want the first part, which is the line, and the first part of that, which is my list of points. I'm going to save that into a variable and make a short display out of that to make sure I'm getting out the right thing. Yes. Here I have my list of points. So that's extracting the data. What can you do with data like that? Well, I love the interpolation function because I can take any set of points and try to create an interpolating function out of this. So I'm going to call this interpolating function something like extract. And it's going to have a parameter of t. So now I have my interpolating function. I'm going to go a little bit wild here and take on that question about using a set of xy points to create your revolution plot. So here's the range that I'm going to use for my plot here. So this plot, if I just plot a regular fashion univariate function with t being my range, I should change that to x, or min and max, so that it's easier for me to write this out. So here's the plot of the curve going through each of my points. And just to make sure I'm not cheating here, I can list plot all of my points. And if I want to see these two functions together, I would just combine the previous two outputs. And there you go. All the points are hit by my interpolation curve. So I'm able to plot my interpolation curve, so nothing is preventing me from plotting the revolution. And I have the revolution for the range for my plotting, and revolution axis that I want to plot is the x-axis. And booyah, there you have it.
Fantastic. Yeah, there's some great examples there of how you can do everything.
Yeah, slight comment here. If you see the example there, the interpolation, so Faisal uses our default interpolation method, which might not be that desirable when you see that there's like a peak, like not sharp portion,
like,
right?
yeah.
To avoid that, we can easily use interpolation, and comma option method goes to spline. Then it actually will smooth it out. So a little bit nicer looking, I guess. Yeah, string spline. Yep.
That does look nicer.
Yep.
Neat.
Great.
Oh, fantastic. Some great examples there. All right, Yu-Sung, I have a couple quick questions for you here as we slowly wind down time. Could you show an example of advanced 3D graphics?
Oh, that's not a simple question. Okay. So yeah, well, we happen to have actually the course called the Advanced 3D Graphics. So I just grabbed that notebook and show it. Just go through. It's a two broad topic right now. So I will show you, showcase what you can do with the Mathematica, especially 3D graphic combined with the, this interactive technique. So yeah, I mean, this is a typical scene of the stage, right? And I'm pretty sure somebody grabbed the Maya or the 3D Max to create this, right? It's pretty sophisticated computer graphics. It almost looks like real. Now, same scene, of course not that. I mean, I don't have time for this, but this looks like just a static picture, although you just realize this is actually a Mathematica scene. See? So Mathematica provide all modern the graphics facility you can think of. Of course, you can move around things. You can get rid of some of the things, like and these things. It's completely written in Mathematica. You can see, so the advanced 3D graphics. I'm a graphics person, so for me, it's a couple of things in the modern, the world. So proper lighting model. Mathematica support all 4 different lighting models that you can find in other, computer graphics language. And then another one is translation and transformation of the object, which Mathematica also support, right? So for instance, that cow case, it's not like computing the cow in any other direction. I just translated it according to the some value based on slider. Of course, lighting, you can see. Another one, which is great addition to version 8, is a texture, as you can see. We have a nice looking floor and the wall, which is actually based on real textures, right? So I can quickly go through. So we have a lighting model which supplies all different ambient, directional, and a point and spotlight. Each light model we don't have a time to describe it, but I made a nice nice looking examples to describe how this lighting model works in each situation. The point light model, same story. It's it works like this. Advanced properties like distance, how the lighting changes according to the distance, And then we have a spotlight, which is kind of interesting, right? Instead of the other 2 lights, it has a more limited version of it. Now, how this works with there's a lot of different topics. How this works with the dynamics, for instance. So this is a good example. We have a very sophisticated camera model that we can control, viewpoint, view angle, any aspect of this camera model, you can change it around. So you can see, this is how it works. So you have a viewpoint changing in here, as you can see how it affects the graphics. You can actually see the effect. Now, how it works with the actual coding. So let me see if I have the code for that. Yeah. Okay. So this is just simple model. You can interactively control in Mathematica. We have a function. So when you want to do that, you mouse over the picture, then click your, for the left mouse button, or in my case, just the D mouse button, and then you move around. Now you can do a panning by clicking Shift and the button, and you can do a zooming by Control, right? Yeah, Control or Command on Mac, I believe, right? So you can do this interactive control. Now, if you want to take, I love this viewpoint. I want to just get the value out of it. What you can do is taking the options. The slash means, it's a, postfix syntax. So it's nothing more than just same as just this, You do this, and voila, you get your view angle, view center, viewpoint, any values that you want to use. You can reuse it on other graphics and such. So, and I highly recommend, if you're really interested in graphic courses, this course explains a lot of different things, texture, how you want to play with the texture, surface properties, and everything is actually using the dynamic interface we just tried to describe here. So I think it's a very good, good course to go through if you are really interested in. And this course is featured in the Wolfram training site. If we go to the general Mathematica site, there's a topic called Advanced 3D Graphics. And it's only 30 minutes, and I bet it'll be well spent 30 minutes for you if you're interested in graphics.
No, great. And if you want to find those, it's wolfram.com/training. We're going to go back to Chris here for one. What kind of visual feedback, a progress bar, a spinning cursor, could a user get while data is being processed by the model?
Yeah. There's 2 constructs that make that very easy. One is called monitor, and the other is called progress indicator, and you can use them together. Suppose I'm doing a calculation that takes a long time to do, so I'll make an artificial one here. I'm going to make a table of I as I goes from, say, 0 to 10. Okay, and I'm going to make it slow by putting in a pause here. So I'm going to pause for, I don't know, 1/10 of a second every time it computes an I, so it's going to take a second to compute. Okay, if I want to see what's going on while it's happening, I can just wrap this in monitor table and show me I while it's computing. And now when I evaluate this, it'll show me I counting up, and then when it's done, it shows me the result. Monitor is sneaky. It actually goes inside this table and picks out this localized I variable and lets you display it on the outside. Now, if I'd like a progress bar instead, I can wrap this I with progress indicator, and I want 0 to be uncompleted and 10 to be completed. And now when I evaluate this, I get the progress bar showing how long it's going to take to finish up. Well, so progress indicator is actually useful in other contexts as well. Suppose I have, say, a dynamic module. I'm going to localize I here. I equals 0. And make a column, say. And I'm going to put the column of 2 elements. The first one is going to be the progress indicator. And the second one is going to be a slider. And I'm going to make that respond to I, or control I, and I'm going to make this progress indicator also dynamic. Okay, so now I have a progress indicator. Oops, I've got the scaling wrong. Let's make that go from 0 to 1. So now I've got the progress indicator tracking my slider. I'll use this opportunity to show you another technique which is useful. You can use dynamics to trigger themselves. So suppose I have dynamic of if I is less than 1, increment I by 0.01, otherwise give me 1, okay? So now this one runs itself. What happens here is this dynamic is going to wake up anytime I changes, but every time it wakes up, it changes I. So it just keeps triggering itself, and this dynamic runs itself without requiring any controls. Hands-free dynamics.
Very neat.
Okay.
Very neat. Thank you, Chris. All right, Yu-Sung, we have one more question for you. This will be our final question. Thank you again for all the questions that you have submitted. We would love to keep doing this, but we're going to be out of time here shortly. So we want to get to one more. Yu-Sung, how do you add a constraint to a dynamic?
Okay, so I think the question itself is also, for a lot of people hard to understand what we are talking about. So I will show you, go through the example. Okay, so far I have been using the manipulate, but in this example I will use the a little bit sophisticated construct called the dynamic module. I think Faisal and Chris already showed you guys how it works. So graphics, it's I will quickly construct dynamic point. So I specify the point. I will put a circle on it, and this is it, right? So this is one dynamic example. We have a mouse pointer here, right? It moves around, right? It's free. Now the constraint means, let's say I want to move this around, but just on the top of the circle. I don't want to move it around actually. I want to just make it in such a way that it just moves around the circle. How are you going to do that? That's it's very nice property with dynamic. Dynamic can get a second argument which can control, how the dynamic behave when it is being evaluated. So again, the same construct, it takes a pure function that's very specific. And what I'm trying to do is, instead of giving the value of the mouse, the position directly, I want to control it slightly differently. So in this case, so the hash sign, the slot, we call it slot. That means it's a current mouse position in this particular case. And instead of just using the value, I normalize it. Well, you can see, normalize is a very neat, handy technique. You normalize it, it will be always on the circle, right? So, oops, what did I do wrong? Pair numbers.
The ampersand.
Yeah, outside.
Yeah.
Yeah, slightly tricky. Okay, we got it. So you can see, we move around. Oops, yeah. It's just working on the circle. You can think of a lot of different ways. If you want to put it in the sine curve, for instance, instead of doing this, you can just say, okay, well, I can actually try it, but given the time. So it's easy to, I highly recommend you take a look at Dynamic, the Doc Center Dynamic Reference, which has a lot of these different examples of constraint dynamics.
Great, fantastic. No, I think that's a great question to wrap things up on.